Hi there YouTube, and welcome to the next part of this tutorial series where we take our Toon shader project and extend upon it. So far in this series update, we have done the FBX SDK implementation, we have done deferred rendering, and now we want to do shadow mapping, and then potentially we will do outline shading. I'm not sure whether we will get to it today. It depends on how efficient we really are. Yeah, so we will end the shadow map stuff by actually maybe creating a bonus episode. Maybe a bonus episode here. Rendering mesh pipeline of sorts. Or maybe, yeah, what should we call it? Draw pipeline, draw calls. Let's quote it because it's not going to be real draw calls since it's just an API here. And it's up to you to actually use the different stuff in the rest of the engine. Okay. So in order to do shadow mapping, you basically render all of your geometry to a depth buffer. So depth buffers is something that we already have. We have a regular depth buffer here. We also have a descriptor heap that actually handles depth buffers. Let's move it up here. And this is something that we should move because it's not related to the descriptor heaps. It's related to the deferred pipeline. Let's see, create R deferred buffers, G buffer components. Anyway, so in order to do shadow mapping, we actually want a separate pipeline. We also want a separate depth buffer. So we need to create another depth buffer slot here on the descriptor heap, and we should remove this since we actually already implemented another interface here. Get CPU handle 0 here. So let's do depth buffers. And let's call it depth buffers. And let's create an array here. And let's set the first one here. And of course add the S. And then down here, we have a problem somewhere, don't we? Oh. But we should also, no, it's handled through the descriptor heap. We're not binding anything. Okay. So let's do something like regular. And then let's do G buffer. Let's do G buffer render target number. Okay, and let's create a shadow map depth buffer. Okay, and let's do a const expression here on sign int shadow map resolution. Let's do this many pixels, and let's create a depth buffer with this resolution. Let's reset the format here. Let's choose another format. Let's do a D32 float with no flags, and let's create the descriptor for it. Okay. Shadow map depth buffer. Okay. The thing is that we also want to be able to, like these render targets here, we also want to be able to actually create an SRV for it. Let's see. Also, we should actually set the DXGI format here and fill out that format here. And let's add this and set it as a standard value to this. Okay. Also make it const. Okay. So this should still work. Oh, we have a problem with that. Okay, didn't I? Oh, there we go. Okay. We have some other problems. Let's see. Oh, I need a different format, I guess. Okay. Let's see. Is this better? Yeah. Okay. But as I've mentioned, I also want to be able to create a shader resource view. Let's see. Let's actually make this public. I think I did that. Okay, we can call create SRV. Okay. Also, our descriptor heap for our SRVs is going to have to expand. And let's rename it CB MCB SRV UAV descriptor heap. And let's move it down here. There we go. So let's we added the space in it. So let's create the SRV here. And let's do device create shader resource view here with our depth buffer here. And our get SRV. And let's do our CB UAV descriptor heap, get CPU handle, and our fourth descriptor. Let's see, we have a problem somewhere. Oh. Okay. Let's see. Let's see. Okay, can't be used with a shader resource view. Let me see. I can't remember how the let me just see. Let's see. In order to create the okay, we need a separate SRV here. Let's do a D3D12 shader resource view here. Texture disk. It's because we can't use this. It's reserved for only depth sensors. We will create. We can move this back then into the private section. Let's use a lot of it. And instead of this format here, we will change it from a depth to a red. It's basically the same. It's mapping to the exact same thing. And we will only have one MIP level, which is the most detailed one. And we will use this texture description instead. Okay, should be fine now. Yeah. Okay. So we've created our resource. Next, we need to actually create a pipeline. We also need something else, actually, before we forget, or I forget. We have our depth buffers set up now, but we also need a viewport and sysdirect. Let's do a shadow map resolution up here. Because we're going to use that for our stuff here. Okay, let's do 2 of these. And a regular viewport. Let's set it all to the and then we will do the shadow map one. Maybe let's just whoops. So this is fine, but this is going to be shadow map resolution and shadow map resolution. There we go. And then we need to fix our viewport here. Okay. Then we need to come, or rather create our shadow map pipeline. So we will be using that one. Let's see, render API here. Let's create a D12 pipeline state, shadow map pipeline. Let's see, deferred pipeline stuff. Shadow map pipeline. And let's find a function where we can actually initialize as a shadow map pipeline. Void initialize shadow map, shadow mapping. And let's do initialize shadow mapping with our device here. And let's set our name, shadow map pipeline. Let's see. Let's create some stuff here. Let's just copy this, I guess. No, not this. Let's copy the original one, because this mostly resembles that. Okay, so let's create a series of shaders for this. Shaders, shadow map. Let's create a vertex shader. I don't think it needs a pixel shader, but let's see, shadow map. Does it need a pixel shader? I don't think so. Let's see if we can do like that and then duplicate these and set it as a null pointer and this as a null thingy. Let's see if I shouldn't be able to compile it because, oh, I can't use it at least because right now it has a rendered target. We should set a rendered target here to 0. Also, I think we only want our position here. So we only do one element. We do the rasterization stuff. And then we need some rasterization information here. So oh, DXGI format D32 float. Let's see. Is it inside rasterize state? Yeah, depth bias, clamp, and so forth. I can remember the standard values. But this is basically if you get too big of a slope on your shadows. For instance, if the angle between the shadow casting light and the object gets too big, or it's over big slopes, you need some kind of like bias to apply to all of the depth buffering. I don't know if I explained that correctly. Feel free to leave a comment or something if you want me to elaborate. Let's see. Yeah, usually. Yeah, you can play around with these values here. Let's see, slope scaled depth bias. As you can see, it's really pertaining to slopes. Okay. Okay. We have our pipeline. Okay. And our pipeline here actually needs the light position. So in our scene here, not material allocations, we set a main lights with the direction that we actually update in our simulation here. So we store it in our current frame lights, and our current frame lights is then direction. Okay, so we have some shadow casting stuff here. That we use. View projection, current frame lights. Yeah, we need to modify this pass data here. Scene light. Yeah. Yeah, we definitely need to modify this, but we will do so in just a moment. No, we should do it now. Let's see. Light, view, projection. So we want to render the whole scene from the perspective of the light. That's basically what we're doing when we're shadow mapping. Let's see. And this is planar shadows. Let's just light, view, projection here. Maybe we should do a common include file here. Common HL HLLSLI exclude, but let's open it and let's do something like this: struct pass data, light data. Okay. Let's do object data as well, and then okay, let's do an include here. Comma dot HLSLI, right? Yeah. Let's just close this for now. So this is our vertex shader here. This doesn't use any of it, so it doesn't care. And let's do remove this. Great stuff. And deferred here. Let's do remove this. Pixel shader doesn't, oh, it uses some of it. At least it could. I don't know. Maybe it doesn't need to. And the base here. Okay, let's see if we can run stuff or if we have crashes. We don't have crashes. Is it always starting out black? No. No, I'm guessing I have a mistake somewhere. Oh yeah, of course. Right now our updating method doesn't do the computation correctly on the CPU side. This is not. If we do like this times 2, right? Will be good. Yeah. Okay. Let's do draw to shadow map. And let's bind. Hi, how are you doing? Let's set all this stuff here. Maybe even like this instead. I'm just recording a tutorial. Let's see. So let's do the shadow map pipeline here. Shadow map pipeline. And then we don't want the clear color. Clear the depth buffer for the shadow map. We don't want a render target. We don't want that either. Let's see. We need a DSV handle. This should also change because it's gets CPU handle here for the first depth thingy. So, okay, let's copy some of this here. And we, of course, shadow map depth buffer here. Let's do 0 and a null pointer here. So we clear the depth buffer on the shadow map here. And we bind our pass data. Let's see. Let's do the first one only. Just for now. Let's draw that to our shadow map. And let's see if everything runs. Everything runs. Okay. Let's update the shader stuff here on the application that we're actually going to run through RenderDoc here. So let's check if, whoops, let's close it and read the capture here. Okay, so we have shadow map pipeline, shadow map depth buffer. Right now it's not rendering anything because, again, we haven't implemented a vertex shader. But it's at least not bugging out anywhere. So in our shadow map vertex buffer here, we basically want to do some kind of transformation, like in our base pipeline here. So let's copy most of it into our shadow map buffer here. Let's see, does everything run? No. Oh, normal. But the, oh, of course. let's not name it. Let's just keep it because it will be there in our information. Let's see. Oh, okay. Okay, so what I did here, where I kind of removed the normal, we need to keep it because yeah, it can't ignore it from the input assembler, I guess. So let's just add it back. I wanted to like ignore it here, but since we have vertex data for all of our meshes with attached normals to each vertex, I guess we can't like, you know, get around it. So let's just pass it in. It doesn't really matter. We're not going to pass it along anyway. Okay, time to open render doc and see what we get. Let's see. So in our depth buffer here, you can see that we actually render our object, our first object here to our depth buffer. So that's basically first part of our thing. But right now we're kind of like using the view projection of the camera, and we want the light view projection. And yeah, we could just, yeah, this is fine. Let's do, yeah, this is fine. There's no need to modify it. Okay, so we need to upload something to our view projection here for our, what do you call it? Lights. And right now, our lights is floating around our scene. We start out by initializing it, but in our simulation here, for our deferred shader here, deferred lights here, we see that we sample the light direction in the actual light. In our light structure here, we have direction, position, and strength. This is a typo, but I'm not gonna bother fixing it. So we need to compute the view matrix. So for a camera, we do, let's see. This is the object transforms. We don't care about that. Shadow transforms. We will be disabling this because we're not using planar shadows anymore. So what's this camera matrix stuff? There it is. Just look for the proper headline. Okay. So basically we calculate a view matrix by calling lookat, and I think that's a fine way to do things. And then we need a perspective matrix. Since we're doing an orthogonal light, we're doing a you know, a quote unquote sun that is rotating around the scene. We will not be using a perspective matrix, but we could definitely do something like this. Let's grab the code. And after we're done, actually, let's see, shadow map. Maybe we should do shadow map for itself by itself. Okay. shadow map computation, and let's comment this out because we don't want the exact code, but we want something like it. So view projection matrix. We're gonna create a temporary no matter what. Let's just compile the pass data, right? I mean, let's do pass data, pass data. Let's see. This doesn't matter right now. So let's set our pass data view projection matrix. Copy. Do we store it on the? What did we do? Is this? No, the camera doesn't move. So, but in case we wanted to like move it, let's just make sure that if we ever update the view projection matrix, we would get a moving camera. Then let's add the scene light. And let's do the yeah, and this would just be our pass data here and pass along our pass data and not do anything to this. Yeah, let's disable this. Let's see. Yeah, everything's still fine. Okay. So let's compute the shadow map matrix here. Um, okay, so let's initialize this XM matrix here, view projection matrix. Now we actually have that right here, light, and it's initialized as a identity matrix. So let's do XM vector DirectX. For a shadow map to render, we want a scene center, which we will set to the origin. And then we want a view matrix for the lights. Matrix view lights. And let's do a XM matrix. I need the DirectX. XM matrix. Look at left hand because that's what we use in this situation. And it immediately wants our light position. Let's see our lights here. we want to load a position, but we actually want to kind of like compute a position. Because our position might actually be our, well, maybe not even be set. So light position, but we would pass in our light position. We would pass our scene center here, and we would pass a up vector, and that's obviously our y. And that would compute us that would compute a view matrix. Let's do a shadow map radius. Let's do 15 or something. So we also want a radius for a shadow map. And let's see, does DirectX have a XM matrix? Orthographic. DirectX math. Oh, orthographic. Yeah. Okay, let's try that. XM matrix projection equals DirectX XM matrix orthographic left-handed, and let's do our shadow map height and 0.5 if and maybe this 200 or something. We should play around with it. Okay, uninitialized memory, of course. Let's see our position. Do we actually update the frame direction? Yeah, we can compute it from let's see. DirectX XM vector 3 scale and let's do DirectX XM load float 3 from our current framelights.direction, and let's do our shadow map radius here. Okay, and then our pass data dot light view projection is the view times the projection. Let's do that. And we should upload that to our GPU and during the next part of this. So let's clean up this. Okay. And let's see. Let's remove that. Okay, and inside our shadow map vertex shader here, instead of we're already assigning the light view projection. So let's try compiling all of this and see if it runs. It runs. Let's see in render doc if I update these shaders here. Whoops. There we go. And in render doc, let's see what our output is. So let's see depth buffer here. Okay. Something is definitely not working. Depth only pass here. Let's see. Vertex shader out. Yeah, we end up with some weird vertices. Yeah, so we're definitely not doing things correctly. The input is correct. Okay. Let me see. What's the problem? Let's see our pass data. Oh, maybe I didn't name it. Material buffer. Okay, let's just name it. Pass data, constant buffer. So pass data, constant buffer. Let's view the contents. Float 4x4, float 4x4, and then what? Pass data. Light. Float 3, float 1, float 3, float 1. There we go. Okay. So our camera stuff is fine. But it doesn't seem like we're actually... okay. So our computation might be wrong. Let me just debug this then. Oh. What's the assert then? I direction. Yeah, so it's not 0. Okay. Let's see light position here. Oh, maybe not look to, look at, right? Yeah, exactly. Okay, now we can run in debug mode. Let's rebuild it and let's look in render doc. Whoops, not the pass data necessarily. Shadow map depth buffer here. It's like it's rendering something very, 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 very far away. Very, very, very far away. Okay. So what happens if we set this to 1 and look at our render doc stuff here? Shadow map, depth buffer. It's still very small. It's still very small. Yeah, I don't think this orthographic thingy is very good for shadow mapping. Let's just do 20 here. Oh, I shouldn't close render doc in between. It's just a habit. It's of course from the side of the object. Okay, let's launch the application again and see the capture this frame. Let's see the depth buffer now. Yeah. I would want to see light position here. So we're very close to the origin. I don't like that, so let's see. We might also be on the wrong side here. Let's see, past data scene light, position is not set yet. Past data scene light. Position is never set. But the direction is like negative on the Y, so we want the position to be opposite of that. Yeah, so it would be minus 0.99 something. The light position here should be, yeah, okay, so it should be flipped. Let's do a negative scale here for 1. And let's see what we actually end up with in terms of our render doc output. I think I should change this function and implement it manually. Well, maybe this ain't too bad. Okay. We'll use it for now. Okay. And we can always fiddle around with that. So let's draw the second one as well, but not the floor. We don't want the floor to be rendered into our shadow map. Okay. Then our shadow map is actually something that we want to access in our pipeline, or rather our shaders. So let's expand this range here. Right now, the SRV for our shadow map is bound to the 4th slot in the descriptor heap. So maybe we can do this. We can do this. So it should be bound. So if we in our post effects deferred lights here did a copy of this G shadow map buffer, let's see, we actually don't have any problems. Let's see, and let's do a float shadow factor equals the G shadow map buffer sampled by our well, our linear clamp here, I guess. Yeah, clamp. Ah, now we need to do some lighting computations here. Yeah, so now we can change the we can actually use a G buffer here, or rather a position buffer. Float position. And let's sample our G position buffer with S point clamp here. XYZ here. Okay. And then whenever we want to do we also need to bind our maybe we even want, so let's see, number of descriptors 5. Do we have a problem right now? No, it's not whining because the driver handles a lot of stuff in root signature 1.0. It's way more simple. Okay, so in our render API, we would actually want our descriptor heap here to hold our regular depth buffer as well. Because right now in the forward render pass, we can't really sample the depth of the object. So let's see, depth buffers. I guess. Yeah, actually, let's move this. And let's do this scope then. Also, this should get this shader resource here. And we will simply use the same thing, although does it have some kind of like, yeah. Let's see. New norm. There we go. And then we'll of course create a shader resource view for that. So let's copy this line here and of course set it to this one. And of course get this. Okay. And we're still good. Okay. So what we want to do inside our pixel shader here is this is of course moved down. So let's do a duplication of this, but bind it to this, and let's do depth buffer, G depth buffer. Okay, and let's do a let's see. I don't know how to sample that actually. Right now we're not using the stencil, so yeah, maybe I just want to change it. Let's see. I actually never tried sampling. Uh, can I do? Oh, I can do red 24 then. Maybe red 24 or what? Red 24. Yeah, this one, I think. Okay. Let's try doing that then. Does it whine about that? Yeah, it does. Okay. Let's see if I can sample it anyway then. Okay. Let's do float depth. Let's see. G depth buffer here, sample, S point clamp, and our input UVs here. R value here. Let's try that. Maybe. Okay, I haven't implemented a shadow mapping algorithm in a deferred renderer before, so let's see. Uh, let's do the calculate shadow factor here. Calculate shadow factor with a light space position here as our input, and return for now just float, maybe just one. Okay. And we might need another sampler for this. But let's first create a matrix that can convert to UV coordinates. And let's do float force 0.5f. This is because we want to be able to convert our light space. Whenever we take our pixel, we know the position of the object in world space, and we want to use that position and transform it by using the lights view projection matrix into light space position. So if it was like looked at from the lights position, but then we only have a shadow map, a depth buffer, a 2D buffer. So we want to transform those 3D coordinates into something that is on the 2D plane of this texture here. So that's basically what we're doing. We're manipulating the X, Y, and Z axis. The C is just staying, as you can see here. And then we're translating, offsetting. So that's basically it, what we're doing. Let's see. So we want to reduce, yeah, like that. Yeah, we want to manipulate the X and Y components. This should be in clip space, mind you. So light space is maybe not light. Clip space pos is actually what we do when we multiply a world position with a light view projection matrix. So let's do a float for computation UV coordinates is equal to multiply our light clip space position here with our two UV coordinates matrix. And let's width and height. Let's grab our width and height here. And let's do our G shadow map buffer get dimensions, width and height, store it. And let's see how many pixels should we do delta over. We're going to sample the shadow map. A float version of the width here. And let's create a kernel. Float to, whoops. Float to And it's also going to be const kernel let's do float2 minus delta coordinate minus delta coordinate. And then of course the next one is going to be 0. And then the last one is going to be plus and then 0. And this is going to be 0, 0, the middle one. And this is going to be positive, positive, positive. And we should be good, right? Oh no, this one needs to go to 0 as well. And this one, let's see. So this is our kernel. And let's do light accumulation equals to 1. And then a for loop here. Let's do, can I do const expression? No. Kernel size. And let's do unsigned int. Can I do this? Seems like it. Okay. And let's unroll this loop here because we will already know the size. It's just me that is able to write it faster like this. I equals 0, but I needs to be lower than the kernel size, and then I++. And then we want to accumulate some lights here by doing shadow map buffer. Oh, we have a special sampler for this. Okay, yeah, so that's the, let's do light accumulation divided by a float version of the kernel size here. Okay, let's wait a minute. So let's implement the shadow map sampler in our root signature. Let's just do, let's do 3 here, but let's increase this. Let's see, and the sampler. The sampler. Let's copy this. We're gonna do this. Let's do D3D12 filter comparison. Min magnify linear midpoint. And let's do address mode border here. Whenever we're outside. Let's do register space 1. So the shadow map sampler will be in our register space 1 here. Let's do max anisotropic filtering like this, less equal. And let's do a border color of a static border color white, meaning fully visible. All right, so this should be our, let's see, This is the samplers. Space 0, space 0. And let's do a sampler comparison state. Shadow map, compare, register S0 space 1. Right? And let's sample our sample compare level 0, which means the MIP map level 0. And let's do that. And then our UV coordinates plus the kernel with the index of I. And then our UV coordinates C. And let's pass out our value, yeah. Oh, whoops, .xy. And we're ready to float for object pos light clip space light equals multiply by RG pass data light view projection matrix times our float 4 here position and 1. And then let's sample a shadow factor equals to our calculate shadow factor here with our object position light here. And let's see, so how do we actually output the color itself? Okay, if we do shadow factor here and simply run it through the albedo, we suddenly have, is it more correct shading? Or is it in whack? I'm not sure it's correct, but it's at least something. Okay, so we have the shadow factor and the intensity. Maybe we want to use them both. Let's do intensity. And then we're totally black. Well, that doesn't look too bad, does it? The whole scene is just fading out, right? Maybe we want, instead of multiplying this. Okay. let's play around with the lighting computation here. So we have our shadow factor, meaning that for each pixel we know whether it's in shadow or not. Which is why we're kind of like, when we do this, maybe even if we do render the floor, we would get shadow then, I think. So let's render the floor. Do I render the floor on the shadow map? No. So let's do that. It obviously doesn't work. So now it's under the scene. Yeah. Let's not render our floor. And this is because it's below. So it's kind of like casting a shadow down below. Yeah, so this is more related to our simulation, I think. Yeah. Yeah. So it's our simulation, not our shadow map per se. So when it's above ground, it's casting shadows as is. Maybe okay. So in order to use our intensity, we could do some intensity steps. Yeah, you could obviously mess around with how this is computed. We could also do something like a diffuse color of sorts. So float color. This is just a basic factor that is. Let's do factor here instead. Okay. So we have a factor calculated from our intensity. Let's do a color here, which is equal to our shadow factor times our albedo plus our intensity times our albedo, and maybe divided by 2. And let's return the color. Yeah, so we have the combination of the shading with different intensities. And of course, everything looks pretty weird when the lights is below our scene. Maybe this is shadowing for this one. I can't really see. Okay. So that's pretty interesting. We actually don't need the depth here right now. But this obviously could also sample a lot of different stuff, like do sampling on the actual position and stuff like that. So you could do a lot of pixel shading stuff here inside this gbuffer merger or whatever. Maybe times 0.5 and then divide only by this. Or maybe okay. Yeah, you could play around with this stuff. Anyway, we've created shadow maps in our gbuffer here. So we sample this shadow map as we usually do. We calculate a shadow factor from this directional light. And we have our samplers, we have our different gbuffer information here. And we can do some Toon shading eventually, and then some wrap up of the whole process here. So what we would like to do is maybe some draw calls here. Maybe we should use the last scene. Let's not do this. Let's not wrestle around with this anymore. Let's do outline shading plus cleanup of the old unused stuff. And maybe we do these things together. Maybe we do a final episode where we are able to actually render a FBX model or something. Anyway, that's it for this episode. Hopefully you found it inspirational, helpful, entertaining, or something of the like. Please consider supporting the channel by commenting, subscribing, or even checking out the description down below if you want to support the work. Anyway, please take care, everyone, and hopefully I'll see you in the next one. Bye bye.